we are asked to find Vout over Vin in this non-inverting op-amp configuration. Now, the first step that I'm going to take is identify the important nodes, the nodes of interest. It's these two. I name this X and I name this N. Step number 2 is to perform KCL on these two nodes. And you see why I didn't pick this node 2 as a node of interest, because I have to do a KCL here, all right? There's a current here flowing from this node all the way inside the op-amp, so it wouldn't make sense to do a KCL here because I cannot really calculate this current. Doing KCL on X, I resist the temptation to write currents here, I1, I2, I3, I4, I5, and things like that. And I will write it in the form of Ohm's law. So, for example, R equals to V over I, therefore I is equal to V over R. Therefore, doing a KCL on X, I'll say that we have the following. Vx minus V out over R is the current flowing from here to here, plus Vx minus Vn over 2R, alright, the current flowing from here to here, plus Vx minus 0, alright, the voltage of the ground is 0, over 5R. Now, doing the KCL on node N, I'll do the same thing. Vn minus Vr over 2R, the current flowing like this, Vn minus Vx over 2R, Vn minus 0 over 3R. Now, how much is Vx? I can calculate this. I can have a useful expression for this, and that is that Vx is equal to Vin. All right? Why? Because I'll assume that the gain of this op-amp is very large. Your exercise will tell you if this gain is large. 99.9% of the times it will be. All right? If the gain is large, we can simply say that this point has the same voltage as this point. All right? Step number 3, as you guessed it, is to eliminate the unknowns of my system over here. So I know that Vx is equal to Vin, all right? Therefore, I now have to find Vn. Now I go to equation number 1. I perform the basic algebraic operations here. I eliminate R. In your exams and exercises, probably for these configurations, they will give you resistance values or a value that is a multiple of a generic resistance, so 2R, 3R, etc. Why? Because if they gave you R1, R2, R3, etc., this calculation would be very, very difficult. The system will be very, very difficult to solve. So, for exams, you probably will not see it like this. You will see actual values or things like 2R, 3R, 5R, etc. So, do basic algebra over here. Vn will be equal to something Vin minus something V out. I did this in equation 1 because I knew that Vx is equal to Vin. On to solving now this. Right, we solve for Vn again, as we did before. We do pretty much the same thing, all right? Multiply with R, separate the terms, and come up with this result. Vn is something V out plus something V in. Now, nothing very complex. Just replace this Vn with this Vn. Let's say this thing is equal to this, all right? This thing is equal to this. And now I'm ready to go to step number 4. You see, in my final equation over here, I don't have any Vn or Vx or things like that, all right? I have only V out over Vin. And as you guessed it, in step number 4, we solve for V out over Vin, what we want, the closed loop gain. So I do basic algebra here, and funny, this thing is exact same as this, all right? Therefore, V out over Vin is equal to 121 over 95, or about 1.27. All right? That was it basically very easy. Just performing basic KCLs on such nodes, all right, on the nodes of interest. And to sum up, we basically followed 4 steps, 4 basic steps. Step number 1, we identify the nodes of interest. All right, these are the nodes of interest. There's also this node here that is not very useful because the current here, or there's a current here flowing inside the op-amp, right, or outside from it. So this tells me that I cannot perform milli KCL here. Step number 2, and I don't have to, by the way, right? We saw that we don't have to do anything extra. In step number 2, we perform a KCL on this node and this node. In your exercise, you will probably have about 2, maximum 3 nodes, right? Probably not more, because this gets exponentially complex as more nodes are being added in. All right, now in step number 3, we eliminate all unknowns. For this system, we had only 2 unknowns. If we had 3 nodes, we would have 3 unknowns, etc. Now we know that Vx, or the node that you, whatever you want to call it, that is having the same voltage as the inverting op-amp input. All right, so this is the inverting input of the op-amp. This is the non-inverting input of the op-amp. If this op-amp has a very large gain, this voltage here will be the same as this, right? Then we need to eliminate all unknown voltages, and then we need to solve for Vout over Vin. Solving the previous system will give us one equation. In this one equation, we will have one Vout and Vin, and we will be able to solve Vout over Vin in respect to Vout over Vin. If in my result I have something like A times V out plus B times V in plus something constant, let's say 10, right, is equal to 0, which would mean that I would not be able to solve in respect to the out over V in this step. It could mean that I have made a mistake. So I must be very careful, all right? If I've made a mistake, it's okay. We return to the previous steps and check where we have made a mistake. The algebra here can get confusing sometimes because there are many unknowns, all right? You must be very careful with the polarities and the signs, all right? And the result then is a piece of cake, all right? And that's it. Click on the op-amp playlist over here for more op-amp videos. Study well and take care.